Hello everybody. We are going to discuss about electromagnetic waves. In this chapter, we discuss about divergence, gradient and curl, surface and volume integrals, Maxwell's equations and Maxwell's equations in free space, electromagnetic wave equations and electromagnetic waves as plane waves. In the surface and volume integrals, we are going to discuss about Stokes theorem, then Gauss divergence theorem. The basic thing we need to know about in this chapter is gradient. Gradient operator is operated on a scalar function. The gradient of a scalar field results in a vector which represents the magnitude and direction of the maximum space rate of increase of the scalar function. It is defined as the space rate of change of phi along a direction in which it is maximum. Mathematically, it is defined as the partial derivative of phi with respect to x into I cap plus partial derivative of phi with respect to y in dot j cap plus partial derivative of phi with respect to z dot k cap. Next, we need to know about is divergence. Divergence is of a vector field represents the net flux diverging or converging per unit volume. It is mathematically defined as the dot product of del operator and the vector field. So it is the partial derivative of component x component of the vector field and plus the partial derivative of y component of the vector field plus partial derivative of z component of the vector field. Okay. When divergence of any vector is zero, it means the amount of flux entering a surface is exactly balanced by the flux leaving the surface. When such a vector is called as solenoidal or continuous. Next, we need to know is curl of vector field. Curl of vector field is the defined as the amount of maximum line integral at any point around a closed path per unit area. It is usually in hydrodynamics is associated with the rotation of a fluid. A vector field whose curl vanishes is referred to as irrotational field. Mathematically, it is the cross product of del operator and the vector field. These are the some important relations involving gradient, divergence, and curl. These two, first one and this fourth one is going to be used in next few concepts. Gauss divergence theorem and Stokes theorem are two important theorems that is used to derive many of the Maxwell's equations. The Gauss divergence theorem states that the surface integral of the vector field over a closed surface is equal to the volume integral of divergence of vector A, where V is enclosed by the surfaces. Stokes' theorem states that the line integral of a vector field around the boundary of a surface is equal to the surface integral of the curl of the field over the surface. Next, Maxwell's equations. Maxwell's four equations are derived from first equation is derived from Gauss law of electrostatics. Gauss law of electrostatics states that the electric flux through a closed surface is equal to the total charge enclosed by the surface. Applying the Gauss divergence theorem, that is surface integral can be converted into volume integral as given below. So now the Q enclosed can be written as the integral of charge density over the volume V. Equating these two integrals, we derive at the first differential form of Maxwell's equations, which is the divergence of vector field E is equal to the rho by epsilon naught, where rho is the charge density. Second equations of second equation can be derived from the Gauss law for magnetostatics, according to which the surface integral of beta ds is equal to 0, which is due to the concept of non-existence of isolated magnetic monopoles. Then applying Gauss divergence theorem, we arrive at the second differential equations form of the Maxwell's equation. Next, Faraday's law. According to Faraday's law, induced EMF across a closed loop is equal to the change in the magnetic flux over through the surface. Then, by noting the potential gradient and electric field relation, we see that EMF, induced EMF, is the line integral of E bar dot with TL bar. Then RHS, which is minus d phi by dt, is equal to the minus d by dt of surface integral of beta ds and then minus d by minus integral of db dou b by dou t dot with ds, equating LHS and RHS in this dm of the E dot dl can be written as surface integral of curl of E bar, which is equal to the negative of surface integral of dou b by dou t dot ds bar. After evaluating, we arrive at the Maxwell's third equations, Faraday's law in differential form. Next, Ampere's law. According to Ampere's law, line integral of the magnetic field along with the line is equal to the mu times of current enclosed in the loop. Applying the Stokes theorem, we see that line integral can be converted into integral surface integral of curl of B bar, which is equal to mu naught times of I enclosed. I enclosed, it can be written as the surface integral of current density dot with the ds bar, where J is the current density, which is amount of charges flowing per unit area per unit time. Then surface integral of cross curl of B bar is equal to the mu naught times of surface integral of J dot ds, which equates to curl of B bar is equal to mu naught times of J. But this needs some correction. The mathematical need for Maxwell's correction to Ampere's law is, we know that for any arbitrary vector, the following identity must be valid. That is the 0. For the electric field, we see that divergence of curl of E bar, which is divergence of minus dB by dt from Faraday's law, which is from Faraday's law. We see that the divergence of B bar is 0 from Gauss law of magnetostatics. But for magnetic field, we see that divergence of curl is equal to divergence of mu naught times of J, but mu naught times of J, divergence of mu naught times of J is not equal to 0. Due to this, we need to modify Ampere's circuital law so that divergence of curl of B bar is equal to 0. The Maxwell's correction to Ampere's law. Maxwell used the basic principle of conservation of charges to modify Ampere's circuit law. Let J bar be the amount of charge flowing per unit area per unit time. Then surface integral J bar along the surface represents the outward flux of J bar across the closed surface. Therefore, surface integral of J bar is equal to minus d by dt of rho dv, which means the flow of charges across the surface is due to at the expense of the loss of charge. Now, applying Gauss divergence to the left-hand theorem, we see that volume integral of divergence of J bar is equal to the minus times of volume integral of dou rho by dou t into dv. This implies the divergence of J bar is equal to minus dou rho by dou t. Then this equation is known as equation of continuity for conservation of charges. Now we see that the divergence of curl of B bar is equal to mu naught times of divergence of J bar, which is equal to minus mu naught times of dou rho by dou t, as divergence of J bar is equal to minus dou by rho t. Then from Maxwell's first equation, we know that rho is equal to epsilon times of the divergence of E bar. So divergence of curl of B bar can be written as mu naught times of divergence of J, which is minus times of divergence of mu naught epsilon naught dE by dt. So now we arrive at the Maxwell's fourth equations. The dimensions of E bar E epsilon naught dou E by dou t is as that of the dimensions of J current density. So this is known as displacement current density. Then Maxwell's equations can be written as follows. This is the equations for in any region. Now, if we see electromagnetic wave equations in free space, we consider that the source terms rho and J are at small region at origin, and we analyze these electric fields and magnetic fields far away from those points. So we see that the rho is equal to 0 and J bar is also equal to 0 in free space. Now Maxwell's free equations in free space written follows. Divergence of E bar is equal to rho by epsilon naught, which is equal to 0, and divergence of B is equal to 0, and curl of E bar is equal to minus dB by dt, and curl of B bar is equal to mu naught times of dE by dt, because J bar is also 0. Now we write the equations of electromagnetic waves in free space. Now we operate curl on both sides of Maxwell's third equations, which is curl of E bar is equal to minus times of dou B by dou t. Applying the curl on both sides, on LHS we observe that curl of E bar is equal to divergence of gradient of divergence E bar minus del square into E bar. This is from this equations which we already saw in the important relations between divergence gradient and curl. We use these to solve the equations. Next, considering RHS minus dou by dou t of curl of B bar, which from Maxwell's fourth equation we see mu naught times of epsilon naught into dE by dt, and J bar is equal to 0 for free space. This is one of the equations of electromagnetic waves for electric field in free space. Now let's derive the magnetic form of the electromagnetic wave equation. Operating curl on fourth equations that of Maxwell's equation, that is curl of B bar is equal to the mu naught times of epsilon naught of dou E by dou t. Applying curl on both sides and using the previous formula, we arrive at the another equation, which is del square B bar is equal to mu naught times of epsilon naught into dou square B by dou t square. This is when we compare this result with that of the general wave equations, we see that 1 by v square, that is v square is equal to 1 by mu naught mu naught into epsilon naught. Therefore velocity of the wave electromagnetic wave is 1 by root times of mu naught epsilon naught. And when we substitute the mu naught and epsilon naught in free space, we see that the velocity to be 3 into 10 to the power 8 meter per second, which is the speed of light. So okay, solutions to these two equations will be of the form in this form. Will be in the terms of propagation constant k bar and omega t and r bar. So these are the possible solutions for these two equations. Then when we apply the electromagnetic wave in on both, when we apply on this equation solution, we arrive at the general we arrive at the equation k is equal to root of mu naught epsilon naught into times omega. These equations must also satisfy Maxwell's equation in free space. According to Maxwell's equation, del bar dot E bar, that is divergence of E is equal to 0 in free space, which implies divergence of E naught into e power minus k bar dot r bar minus omega t is equal to 0. This implies del divergence of E is equal to 0, and we apply this formula relation to derive some important results. When we apply this equation, that is divergence of a scalar function times vector field is equal to the gradient of the scalar function dot with a bar plus scalar times of divergence of a bar. When we apply this equation, we see that the second term of this vanishes as the divergence of E naught is constant, because is 0, because E naught is a constant and operating del operator on this constant function is always 0. Next, we prove that electromagnetic waves are transverse in nature. This is the earlier derived equation, which implies k bar dot with e bar is equal to 0. This means the propagation constant is perpendicular to the e bar. Similarly, when we apply Maxwell's second equation, we will arrive at the k bar dot b bar is equal to 0. This means the propagation constant is perpendicular to the magnetic field. So both E bar and B bar are oscillating perpendicular to the propagation vector k. So this proves the electromagnetic waves are transverse in nature. It is we can also prove another thing by using third Maxwell's equations. When we apply when we compare LHS and RHS of third Maxwell equations, we and apply this important relation, we see that LHS turned to be I times of k bar cross E bar, and then RHS is equal to I times of omega B bar. Equating these two, we see that k bar cross E bar is equal to omega times of B bar. This implies B bar is equal to k bar cross E bar by omega. Omega can be written as k bar by root of mu naught epsilon naught. So from this relation, we see that B bar is oscillating in direction perpendicular to the plane containing propagation constant and electric field vector. Then plane electromagnetic waves in free space. We see that according to Huygens wave theory, a wave propagates through the repeated formation of wavefronts, plane wavefronts. A wavefront is the locus of all such points having same phase. We now prove that these wavefronts are plane wavefronts for electromagnetic waves. So, at a fixed time for a monochromatic wave, propagation constant dot product with R bar is always constant. This results in the equation of plane. This confirms the plane electromagnetic waves as plane waves. Thank you. This chapter is almost completed, and we'll see in next module. Thank you. Bye.